Hello everyone, I hope you're doing well. This video is about linear functions and graphs of linear functions, which is section 2.1 and 2.2 in the book. We may not get through all of the second section. So in the first week of this course, in the first chapter of this book, we were concerned with talking about functions generally, and we talked about sort of properties and applications and manipulations that are common to all kinds of functions. And today and going forward in this class, what we're going to do is sort of start introducing ourselves to various families of functions that have special forms and special kinds of applications. And the first of those families is the linear functions. So let's start with an example that you see here. So this is a little dated in the age of Uber, but there's still taxis about. So the idea is you get into a cab. They set the meter at $2.60 as soon as you get in, and then you start driving where you're going, and you get charged additionally for every kilometer. So the longer the trip, the further you go. So first thing I'm going to do to try to build a mathematical model of this function, of this situation, is introduce a couple of variables, right? So I'll let D be the distance that I travel in the taxi, and the other important variable here is cost, right? Cost of the ride in dollars. Notice that when you have, when you're sort of modeling a real world situation like this, it's a good idea to be as clear and precise as possible about the meaning of your variables, and also specify units if that's relevant to the situation. Okay, so now I'd like a function that relates D and C somehow. And if you don't see this right away, a good way to go about things is to pick some easy values of one of the variables and try to compute values of the other variable. So here I'm going to pick some easy values of D and see what the corresponding value of C would be, right? So for example, if D equals 1, so this is the case here. So I ride 1 kilometer. Well, then I pay the $2.60 and I pay $1.75 for the kilometer. So that gives me a cost of $4.35 for the total ride. What if D equals 2, right? So this is, and so you can see all I'm doing here is I'm picking some easy values of one variable D, and I'm computing the value of the other variable C, right? So it might even be worth saying here. So this is the value of C. The value of C, and so forth. And notice that when I go 2 kilometers, I pay the $2.60, and then I have to add 2 kilometer charges, right? 2 times $1.75. If you do a few of these, hopefully the pattern becomes clear and you can see the sort of abstract relationship between the two variables, right? So here I do one more. This is the case D equals 3, right? If I go 3 kilometers, I pay $2.60. Plus I have to add 3 1-kilometer charges. And now I see what the idea is, right? Whatever D is, it goes in right here. It just multiplies the 1.75. And this gives me, whoops, that's not what I wanted. This starts to give me a general formula. I can take the values that I have computed so far and put them in an input-output table. So you can see the first 3 columns of this table correspond to the values that we've computed up above, right? The top row here, these are distance values. The bottom row, the bottom row, you can see it is our costs values. There's the 435, right? That's the cost associated with D equals 1, 6.1, cost associated with D equals 2, 7.85, cost associated with D equals 3. And I haven't shown the calculations, but if you did this kind of thing for D equals 4, D equals 5, you get these values in the last couple columns. So what you're doing when you do this exercise is really generating an input-output table for the function. But again, I think from here is where we can see the general pattern. There we go. Here is our functional formula for C in terms of D, right? So here I'm being a little bit loose with my notation C. I'm letting it be the output variable and also the name of the function. You know what, we probably shouldn't do that. Let's give the function a name f and let C be the output value, right? So C equals f of D is 2.6 plus 1.75d, right? The value of d multiplies the 1.75. So this is an example of a linear function, and we will say, why and what makes it linear very soon. But one thing I will note, and this is the defining feature of linear functions, is that as I increase the distance, right, as I keep going an additional kilometer, every additional kilometer costs $1.75. And so this is the function's constant average rate of change, right? The average rate of change of this function over any input interval is always 1.75. This is what makes a linear function a linear function. It has a constant average rate of change. For example, suppose, and this is a calculation from back in chapter 1, right? If I wanted to find the average rate of change over the input interval from 1 to 3, excuse me, we know how to do this. You take the change in the function value. Let's use our proper notation there. Excuse me. Change in the function value in the top divided by the change in the input value. F of 3 is right here, 7.85. F of 1 is right here, 4.35. And when you do the calculation, you get 1.75. And if you pick any input interval you want, you could do this over 2.5 or 1.6 or 4.10 or any input interval. It's always going to come out to be 1.75. Okay, so I'm not going to go through the details of these calculations. Hopefully you're good at finding average rate of change by now. I just want to point out the key feature of this kind of function. And here we do it really abstractly, right? So take an input interval where the endpoints are variables and do this calculation of f of b minus f of a over b minus a. And so there's a little bit of algebra involved because there are variables. But if you do the simplifications, you'll find that everything cancels and you get 1.75. So the key here, again, is this per kilometer charge is the constant average rate of change of the function. Okay, so let's talk a little bit about linear functions in general. This is just a single example of a linear function. Oops. A linear function is a function that has this form, right? So f of x is m times x plus b. The input variable only shows up in that one spot on the right-hand side, right? So I take a number m, I multiply by the input, and I add another number b. And you can see up here that this is what's happening, right? The input variable is d. I'm multiplying it by 1.75 and adding 2.6. So that's called a linear function. So here are two examples, right? So f of x equals 3x plus 4. The m value is 3. The b value is 4. G of x is negative 0.2x minus 200. The m value is minus 0.2. The b value is minus 200. Those are both examples of linear functions. And here is a function that is not a linear function because it doesn't have this very specific form. Right? The output has to be computed by a number times input plus another number. Nothing else is allowed, right? So no x squareds, excuse me, no roots or denominators or anything crazy like that. So up above, indeed, here we said this was a linear function. The m value is what's multiplying the input, right? Notice that it doesn't really matter what order you write the terms in. For this function, the taxicab function, m is 1.75 and the b value is 2.6. And the average rate of change, we just set up above that the average rate of change of a linear function is constant, and it's the m value, right? We saw this in the taxicab example, and this is true in general, right? So for this function here, over any input interval, the average rate of change for that function will be 3. And for this function, over any input interval, the average rate of change will be negative 0.2. Notice that for any linear function, here again is the general form, if I just plug in the input 0, then that first term is going to be m times 0, which of course just goes away. It's equal to 0. So f of 0 is equal to b. This gives us an interpretation of the number b. Right, so now we have an understanding of what each of these numbers, these are sometimes called parameters, mean. The first number is the constant average rate of change. The second number is the function value at 0. And if b is the function value at 0, well, it means that this point is on the graph, right? Because when the input is 0, the output is b. This point is called the y-intercept because it's always on the y-axis because its x-coordinate is 0. And if your x-coordinate is 0, then you're on the y-axis. So b is the y-intercept, m is the constant average rate of change of the function. And I note here that we'll call m the slope, and in just a minute, we'll see why. That seems like a strange term to use at this point. And for now, you can think of it as constant average rate of change, and that's just fine. We're going to link that to slope in just a moment. So the graph of a linear function is a straight line, right? So we know what the graph means. It's the plot of all the input-output pairs in the plane. And a linear function has a very special shape, right? We've seen a bunch of different graphs. They're not all straight lines, but linear functions do graph as straight lines. And the linear function is increasing. So this means as the graph goes up as you go from left to right, if the slope is positive, and it's decreasing if the slope is negative. And we know this because we know that m is the average rate of change, and we know that that a function is increasing means its average rate of change is positive, and decreasing if its average rate of change is negative. All right, so let's go ahead and link average rate of change and slope. If we take 2 points, so notice here, I don't even have a function. I just have these 2 points in the plane, 2, 1 and 8, 10, and I've plotted them, right? So this one on the left is 2, 1, and this one on the right is 8, 10. And if I do this delta y over delta x calculation, all I really need to do that calculation are 2 points. I don't need the whole function, right? So I take change in y, that's the difference in the y coordinates, 10 minus 1, over change in x, difference in the x coordinates, 8 minus 2. Make sure you subtract in the same order. So I'm going right point minus left point. It doesn't matter which direction you go as long as you do the same direction in numerator and denominator. And when I do some math here, I come out with 1.5. What this is measuring is the ratio between delta y, which is this vertical distance here. It's the difference between the two y values, and delta x, this blue horizontal distance here, which is the distance between the two x values. And calling this slope is actually a sensible thing to do, right? Delta y over delta x is sometimes referred to as rise over run, because you can see in this picture that delta y is a vertical distance, a rise, and delta x is a horizontal distance, a run. Well, if there is a lot of rise and a little run, then this is going to be a big number, and this is going to be a steep segment. On the other hand, if we have a small rise and a big run, then this blue thing is going to be a small number, and this is going to be a shallow, not very steep segment. In that sense, it makes sense to call this number slope. When it is big, the segment's steep, and when it is small, the segment is not so steep. And that's sort of, we think of slope as steepness, like the steepness you would feel if you were walking along the segment. And to link this with average rate of change, right? So here we don't even have a function. If we do have the graph of some function like this blue curve, and we want to find the average rate of change over some input interval, all we use are the two endpoints of the interval. That is, we're actually doing the same calculation we did up here. We're just picking 2 points off the graph to do it with, right? So delta y over delta x, you can see in the display down here, is f of b minus f of a over b minus a. We're very familiar with that formula by now. And the numerator, f of b minus a, is just the vertical distance between these 2 points, and the denominator b minus a is the horizontal distance. That is, average rate of change is a slope. It's a rise over run between 2 points on a graph. It's the slope of what is sometimes called the secant line to the graph. So you don't really need to know that fancy term, but a secant line is just a line that goes through 2 points on a curved graph like this. Okay, let's look at some examples and maybe talk about graphs just a little bit. Can we find a linear function whose graph passes through these 2 points? Now, it may seem at first glance that this isn't a lot of information to be given to determine an entire function. We only have 2 points on the graph. However, you've heard the old saw that 2 points determine a line, and a linear function's graph is a line. So this actually is enough information. The first thing I'm going to do is compute the slope between these 2 points, just as we did up above. Change in y over change in x comes out to be 4. So that's my m value. And now I know pretty much what the linear function looks like, right? The linear function has the form f of x equals mx plus b. I know the m value. I don't yet know the b value. However, I can use one of my points to figure that out, right? If xy is any other point on the graph of this line, then if I compute the slope between xy and 720, I'm going to get 4, right? Because linear functions have a constant average rate of change. So when I do this delta y over delta x, I get 4. And if I do a little algebra with that, I just multiply both sides by x minus 7. And don't worry about the colors right now. We'll explain that in a minute. If I multiply both sides by x minus 7, I get this equation. And then I just do a little bit of algebra with that equation, multiply through the parentheses to get 4x minus 28, and then add 20 to both sides. And here we have it. This is the answer to the question. That's the linear function whose graph passes through those 2 points. We can speed this process up using what's called point slope form for the equation of a line. And this right here is an example of point slope form. And you can link up the colored numbers with other aspects of the problem. 4 is the slope that we figured out up here. And then 20 and 7 are the coordinates of a point on the line. And this form always works. That is, if I know the slope of a line, m, and I know a point on the line, x1, y1, then this is always the equation of the line. y1, y minus y1 equals m times x minus x1. And so that's kind of a faster way to get to the equation than what we did up above, although it should be said that this method will always work as well. So for example, if I want the equation of a line with a given slope passing through a given point, then point slope form allows me to write this down in one step, right? What is y1? It's the y coordinate of the point, so that's 6. M is the slope, -3, so that's right there. And x1 is the x coordinate of the point, that's 9, so that's right here, right? And in one go, I've written down the equation of the line, and I can just do a little algebra to clean it up, right? So if I multiply through on the right, I get -3x plus 27, and then add 6 to both sides, and there's my final answer. Okay, let's just look at a couple of these exercises. So these are solutions to a couple exercises in the notes and exercises here. So I'll look at just a couple of these, and then we'll move on to the next section. If you are watching this video, you might want to pause at this point and try these exercises and then come back to the video or the notes to check on the solutions. Okay, so in this first one here, we have a modeling problem, right? We have a population of a town that we're told is growing linearly. In 2005, there are 69,000 people, and it grows by 2,500 people each year. So this right here, growing by 2,500 people each year, that's giving us the constant average rate of change, right? So the m value here is going to be 2,500. And so let's see what's here. So indeed, I sort of do this out much the way we did the distance and cost one for the taxi cab. In 1 year, right? So my t value measures years after 2005. Well, if it grows by 2,500 people per year, then 1 year after 2005, the population is going to be the initial 69,000 plus the 2,500 new people. After 2 years, it'll be the initial 69,000 plus 2 times 2,500 people. And after t years, you get this formula, right? 69,000 plus 2,500 times t. And we can see this is a linear function. There's the m value, the constant average rate of change, and there's the b value, the 69,000. Find the slope connecting a couple of pairs of points. So these calculations in 2.2 are very much like the calculation we did up here. So I won't dwell on the calculations in the video. They are both done here, so you can check them out later on. But given 2 points, we can always find the slope of the segment that connects them. Notice in this first one that we get a negative answer, right? So 2 over -5 is just -2/5. And there's nothing wrong with a negative slope, right? A negative slope is just a line that runs downhill. Okay, so there's a few other exercises here. Whoops, that's not what I wanted to do. There's a few other exercises here that I suggest that you try, identifying slope and y-intercept, finding formulas for linear functions. I'm going to go ahead and move on to the next section. But again, I can't emphasize enough that the way to master this stuff is to practice. And there are practice problems in the book. There are practice problems in the notes and exercises. Do as many as you can. Okay, let's move on into the next section and talk a little bit about graphs of linear functions. So here I have the graph of the function y equals x plus 1. Now we can recognize this a little bit because we know that this second number, the +1 here on the right, that's the y-intercept, which is where the graph hits the y-axis. And indeed, that is where the arrow is now about the y value 1. So that looks right. Now the slope here is also 1, right? There isn't an m value, which means m is just 1. So that means I have a rise over run of 1, right? So for every 1 unit I go horizontally, I go 1 unit up. That's what rise over run means. And that looks about right. If you go 1 unit over, it's about 1 unit up, 1 unit over. Oh, I'm sorry, I have my units off. Whoops. Now, careful of the scale. See how that's a 2? So 1 unit is actually right there. So when I go 1 unit over, 1 unit over, that's 1 unit up, right? So a little bit hard to see. But really the thing that I want to get across here is if I use this slider to increase the slope, right? So now the slope is 1. When I increase the slope, right? So you can see the m value is getting bigger, and notice the effect on the graph is it's getting steeper because its slope is increasing. Right. On the other hand, when I decrease the slope, it goes in reverse. It gets shallower, 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 shallower. Whoops. Right. So here I have a line with a very small slope, 0.05, and you can see it's just barely going uphill, right? Uphill, but not very much. Boy, that's an odd way to display that. Bear with me here while we check out what's going on in the code. So, well, that doesn't help either. Well, let's try this. Okay, so sorry about the diversion into mathematics code. I don't need to see that anymore. All right, so now again, shallow slope, and notice what happens when m kind of goes through 0, right? So here we've got a really shallow slope, but when m goes negative, now the line runs downhill. And as m gets more and more negative, it becomes a steeper and steeper downhill. All right, let's go back to the original line, x plus 1, m equals 1, b equals 1. And now look at the effect of b. Now, as I increase b, what I'm increasing is the y-intercept, which is the y value here where it hits the y-axis, right? So what happens, you can see the line moves up, but it doesn't change its slope any because the slope's not changing, only the y-intercept's changing. Right, so changing b just kind of slides the line up and down, right? And negative values mean the y-intercept is down below the x-axis. Okay, so just kind of to get a feel for graphs of linear functions, if we have a linear function we want to graph, so suppose I have a function like this, notice here that the m value is 1/4, right? X over 4 is 1/4 times x, and the b value is -10, and we want to graph this. Well, in 2021, of course, you can graph this real easily on the web. So this is kind of an FYI, and it is useful to be able to do some things in your head because it speeds up your work a bit. In general, if we want to graph a function by plotting points, we have to plot an awful lot of points unless we know what the function looks like in advance. And that's the case here. I know that the graph's going to be a line. So I don't actually have to plot very many points. I just have to plot 2 points, right? Once I have 2 points, I can put my ruler down and connect the dots and I'll get the graph. All right, so let's just generate 2 points. I'll just plug in some x values, right? Pick some easy x values to plug in. Notice that when I plug in 0, I get -10, but I knew that was going to happen because I knew the y-intercept was -10. But this gives us a point on the graph kind of for free. And now I only need one more point. So I'll plug in 8. I mean, you pick whatever input you want to generate another point. I get the y value -8. So now I have 2 points on the graph, right? 0, -10, and 8, -8. So to graph this, all I have to do is I generated a third point. That was unnecessary, but that's okay. Now we have 3 points on the graph. And once you have your points, you just kind of put them down and connect the dots. So here is the graph. Here's the point 0, -10 over on the left. Here's the point 8, -8 in the middle. Here's the point 20, -5 over here on the right. And again, I know the graph is a straight line, so I just have to connect the dots with a straight line. So graphing a linear function is something that's easy, even if you don't have technology. And of course, today we have all kinds of technology to help us with this. It's worth noting about graphs that another way to generate the graph of a linear function is if you know the slope and the y-intercept. And if you have the formula, then you know the slope and the y-intercept. So here's another example. The slope here is 4/3. The intercept, y-intercept is -6. So the way that I could graph this function is I'll start with the y-intercept. So I know that this point right here where the arrow is, that's the point 0, -6. That's going to be on the graph of the function. So boom, I put a little dot there, right? So there's my first point. And I know that slope is rise over run, right? So a slope of 4/3 means that if the run is 3, that's the bottom number, then the rise is 4. So that means if I start at this point and I go 1, 2, 3 to the right, I'm going to go 1, 2, 3, 4 up. So let me count 4. That's going to go right there, right where the arrow is now. So I can sort of graph the line by taking that little step, right? 3 steps over, 4 steps up. There's another point on the line. And of course, the line is straight, so the entire segment has to be on the line. And I can just keep doing this, right? 3 steps over, 4 steps up, 3 steps over, 4 steps up. I can go in the other direction, right? 3 steps over, 4 steps down if I'm moving to the left. And I can generate the line using a point and the slope as well. Again, just sort of the more we can understand about the graphs of linear functions, the easier it will be to work with them. A word about x-intercepts, right? So the y-intercept is sort of baked into the formula. You can see it staring at you when you're looking at the linear function. This y-intercept is -6. This y-intercept is -10. Linear functions usually have x-intercepts as well, right? So this function here has an x-intercept, it looks like over here. By an x-intercept, I just mean a point where it crosses the x-axis. Finding them is not that difficult. Right, so here's an example, right? I have a function, I want to find both intercepts. The y-intercept's easy, it's 42, right? I can see that from the formula of the linear function, right? Indeed, y-intercept is 0, 42. It's worth noting in general that for any function, whether it's linear or otherwise, the y-intercept is always just the function value at 0. So y-intercepts tend to be pretty easy to find. You just plug in x equals 0 into the function and out pops the y-intercept. To find the x-intercept, well, the x-intercept is on the x-axis, which means it's a point where the y value is 0. So I'm going to set the y value, that's the output, to 0, and then I have to solve the resulting equation for x. So for a linear function, this is not too bad. In general, this could be a hard equation, but for linear functions, it's not a hard equation. So what did I do? I added 3x to both sides to get this and divide both sides by 3, and I come up with x equals 14. So the x-intercept for this function is the point 14, 0. Notice that x-intercepts always have y-coordinate 0 and y-intercepts always have x-coordinate 0. And notice also that if you know the two intercepts of a linear function, you get its graph for free because all you need is 2 points to draw the graph of a line. Here is 0, 42, the y-intercept. Here's 14, 0 on the right, the x-intercept, and I just put my ruler down and draw a line, and I get the graph of this function, f of x equals negative 3x plus 42. Okay, all right, we're getting to about the 30-minute mark, and I want to keep these videos to be not too much longer than that. So I will pick up tomorrow talking about horizontal and vertical lines, parallel and perpendicular lines, and intersections of lines. And then we'll move on and talk a little bit about some application problems in section 2.3. Take care of yourselves, folks.